And everyone else can mute yourself if possible. Okay, so welcome to the Tutte Colloquium. And today we are very happy to have Bill Cook.
Yeah.
So I think Bill doesn't really need much introduction. He graduated from Waterloo many years ago for a PhD. Since then, he worked in many universities and institutions. Bill works on discrete optimization and operational research. Sorry, what is it called? Operational research. And he's famously known for his extensive study in traveling salesman's problem. And I think today he's going to talk about some recent development in this field. Okay, Bill.
Yeah, okay, thanks, Jane. Let me try to find my way. So I have my pictures of my colleagues. I'll try to join them there. And oh, there I am. Whoop, hold on. There. Hey, everybody. Thanks for coming. So this talk's together with Dave Applegate and Daniel Espinosa, who both are now for Google, Marcos Cuculier from Chile, and Kjeld Helsken, who I worked extensively over the past few years on the TSP from Denmark. Let me switch to the front of the slide. The talk will be on the traveling salesman problem. The particular example so it's a big lag. So I'm going to switch to sharing the keynote rather than sharing me. Hold on. Just wait a second, and I should disappear. There I go. I'm going now. So I'll still be on the little side one. So if you want to see me pointing at things, you keep it the side one going. So this particular example, the traveling salesman problem, the tour itself has no application, right? It was the Euclidean tour through some 2 million stars, the 3D locations of some 2 million stars. But it did fulfill a long-time ambition of mine of being written up on the sci-fi network. I'm a big fan of science fiction. But as I said, no application of this particular result. The techniques we use to obtain the result, though, do have a great application. A recent indication of that is that 2 weeks ago, Amazon announced a contest, a challenge, with a $100,000 first prize. You can still register. The contest starts. The date will be posted on March 15th. So it's three prizes: 100,000, 50,000, 25,000. This is not a research grant. This is money. I mean, $100,000 in cash, U.S. cash, that you can take to Tim Hortons and use it. And it's about techniques to solve a traveling salesman problem for routing trucks. And if you read along that little blurb, what they're hoping is that machine learning, deep learning, artificial intelligence methods can be combined with optimization methods to produce even better results. And here their data is going to present the tours driven by actual drivers that might have some particular knowledge of the road. And so that's a hope somehow of combining machine learning type of techniques with optimization to do better. And they're offering big bucks because this is of quite value to them. I think it's all cool, but one thing I take a little bit exception to is that the blog that appears on Amazon Science website to announce the contest, their first paragraph states that the traveling salesman problem is impossible to solve except for the simplest of instances. Right? This is very common. You see this type of remark in many in the popular press that leads to newspaper articles where some scientist gets a good tour for 20 points, and that's a celebrated result. It's a little bit disappointing that Amazon has that. Particularly, they're announcing this big important contest. It's attracting lots of researchers, and this is the first paragraph. So, for example, the simplest of instances. This past September, a mapping organization in the Netherlands contacted Kjeld Helsken and myself and provided us with a distance matrix of biking, pair point-to-point biking distances in Holland between some 57,000 historical points, the historical sites, monuments, and challenged us to find the TSP tour. So they're doing this to show off their point-to-point software, the fact that they can generate such a matrix. So the data is 1.7 billion entries. And it's hard to say that that's a simplest example of the TSP. Like, so even a really low order polynomial time algorithm would be nearly impossible to solve if it was sequential. And if you put on another factor of n or m is the number of edges, and n is the number of nodes, it would be completely impossible. So it's hard to argue that was simplest. But Kelvin and I took up the challenge, and we have a tour that's some 20,000 meters. So 20,000, 20 million meters, so 20,000 kilometers. All right. It's a pretty tour, and they can, with our software, draw pictures of it. But anyone can find a tour, and equipped with their distance matrix, anyone can compute the distance. That's not saying anything. What's special about this tour is that we can prove a lower bound on the length of any tour. And that lower bound shows that our tour can be shortened by at most 14 meters. So it's impossible to visit those monuments in anything less than 14 meters less than what we have solved. Our solution. Now, our solution, Kelvin Helsken is a genius about finding tours. So this solution was found. First, he had a tour that was about 250 meters longer than this. A branch and bound search then produced a tour that was about 150 meters. And then he combined those two tours with a genetic programming algorithm to find this tour that now we're very close to proving optimal. So give us a few days, probably sometime next week, this will actually be solved. So it's currently running on a network of some 320 processors in the third floor of the MC building. Oh, this is not just an accident. Not like we tried lots of examples and finally got them to solve. This is the third large instance that we tried. The previous two, several years ago, we also found the exact optimal solutions. These were walking distances. It's important in our code that the distance between A to B is the same as from B to A. That's why they're biking or walking and not driving on one-way streets. These were instances with a little over 49,000 points for historical sites in the US and pubs in the UK. And this is old school math. It's doing nothing, just engineered and making algorithmic developments on a technique that goes back to the early 1950s with Danzig, Folkes, and Johnson, who wrote an amazing paper on the traveling salesman problem. I'm so in awe in it when I look at it. This past week, getting ready to give this talk, I looked not at their journal version, which is kind of polished, but they have available from the RAND Corporation. You get their original research report. And they solved this 49 city problem by hand. And they had this hand-drawn proof, a single page. They give you a hand-drawn proof that it's short as possible. This is something that newspapers would report is impossible. And yet they did it by hand and give a convincing argument. So they were faced with the same type of problem we have from the Netherlands. They were given a matrix. Right? Their case is 49 by 49, well, only half of it because of the symmetry. And when you're given point-to-point distances, it makes sense to view the problem as selecting edges. If you view it as a graph, the point-to-points are edges. Because you have the cost of the edge. So if you look up in the table, you can look up what the cost between any pair of points. So you have cost on the edges. And so that leads you to have variables for each edge E to have a variable XE. That's 0 if you don't use the edge, and 1 if you do. And if you do that, you can make a algebraic formulation of the problem. You want to minimize a linear function over those 0, 1 tour vectors. So each vector represents a tour. The ones pick out the edges in the tour. Oh, but that looks hopeless. You have nearly n factorial characteristic vector. So that's not directly helpful. But you can apply linear programming, which was George Danzig's baby. And following some earlier work on the assignment problem by Julia Robinson, which was the motivation for that was the TSP, they attacked Danzig, Folkes, and Johnson, attacked the TSP with linear programming. So what do? You just find some linear inequalities that contain amongst their solutions all the tour vectors. So the tour vectors are sitting in space. You find a convex polyhedron that contains them all. You want to optimize the linear function over the vectors. Instead, you optimize it over that polyhedron, over this solution set, the system of inequalities. That's linear programming. that you could do. It doesn't solve your problem, but it gives you something very important. It gives you a lower bound. That's key to trying to solve these instances of the TSP. It's getting lower bounds. So guarantees no one can do better. And that's how we solve those large problems, getting a linear programming lower bound. All right, that sounds great. Linear programming is polynomial time algorithm. We can compute the optimal solution, except when you're trying to solve a practical problem at a large scale, you quickly realize, well, you can't actually solve a linear, well, at least very difficult to actually solve a linear programming problem. I mean, precisely. So when I say this is optimal, I mean it's optimal. You can't do anything better. I don't mean up to a certain precision. I mean, it's the optimal. These are integer distances. So we have, I mean, it's well-defined, the optimal, and ours is optimal. So you're faced with an optimization problem in linear programming that you can't precisely solve, but there's something great about linear programming, and that comes equipped with a duality theory due to John von Neumann. So you have these two linear programming problems, and any feasible solution, so any solution to the dual, gives you a bound on your original problem. So we don't need to solve the problem, we just need to find a good solution to the dual. Okay, you can say, well, how are you actually finding a good solution when you're talking about, you know, various tolerances and machine precision? Well, for the traveling salesman problem and combinatorics in general, your vectors are 0, 1. So you have in your constraint saying you're less than or equal to 0 and bigger than or equal to 1. In a dual problem, that gives you two identity matrices. So you can take any dual solution and make it feasible. So you give me any dual solution, I can, by manipulating the dual variables, possibly with decreasing the bound a little bit, I can find a valid bound. And that's how we get the exact solution. I see this is misunderstood, that the fact that we use linear programming means that we're subject to certain tolerances. Our code can run with any linear programming solver, even if it gives wrong answers. I mean, it'll take a long time if it gives wrong answers, but it'll still be valid. All right, so linear programming problems can give you bounds, can give you good bounds. Well, from convex geometry, the theorem of Minkowski says that convex set of vectors, you can find their convex hull. So the traveling salesman problem can actually be solved as an LP problem. The bound can be exact. The trouble is we don't know what that LP is. And Dancing Folks and Johnson also knew that. And they write it in such beautiful language. I mean, reading their paper, it's like you're reading it's like comparing Anthony Trollope novel from the 19th century to something that you just pick up at the airport here. I mean, look at this thing. They say that it's not only hard to find, but they say that the number of inequalities they're so profuse in number, right? It means there's lots of them. So you have to do something special. You're not going to get them all, but that didn't deter them, right? They just worked with some simple inequalities that you can immediately see are valid for all tours. The first ones are these degree equations. You pick any node, that delta v, any node v, delta v would be the edges meeting that node. Sum of their edges has to be 2, because the tour meets that exactly twice, the degree constraints. You also have called the subtour elimination inequality, or subtour inequalities. Pick a subset of nodes, S. Well, it's a proper subset, the tour has to visit that set and leave, maybe more than once, but at least enter it and leave. So you look at the edge cut formed by that set. So the edges have one end in the set, one end not in the set. Some of those variables have to be at least 2. So this is like the outside cut set form. You also have an inside form of it. Saying you have k points, the number of edges that have both ends in a set can be most k minus 1. These are called subtour inequalities. So you put that together, you have this famous relaxation of the TSP called the subtour LP. And it's a subject to a lot of theoretical studies. The most prominent one is called the 4/3 conjecture, that it'll give you a 4/3 bound for the TSP. Now, Christofides' algorithm, you know that there's finally been a chink in the Christofides armor, that there's a randomized or an average algorithm that gets slightly below 3/2, a big result. So now the question is whether you drive that down to 4/3, and that question is driven by the subtour LP. All right, but Dancing Folks and Johnson didn't care about that. They wanted to solve the problem. Their particular example, the answer was called 699. They got a bound of 697 from, can you hear my poor cat? Hold on. Come on. So the 697 was acceptable for them, but there weren't any more subtour inequalities. Well, how they know that is that they, how do they solve all those subtour inequalities? Well, they first use some of them. If they weren't happy with the bound, they check, well, adding any more of them, would that improve my, I got to get rid of the cat, he's walking on the keyboard. So you use the inequalities, solve the LP. If you're unhappy with the bound, you put more inequalities in. Well, what ones you put in? Ones that are violated by your LP solution. So they keep doing that until they can't find any more subtour inequalities. At that point, they're stuck. Fortunately, Irving Glixberg, another mathematician at Rand, pointed out two complicated inequalities satisfied by all tours. And that's what they report in this hand-drawn solution are the dual variables corresponding to that system of inequalities. They gave you the dual solution that proves it's optimal. So like in the upper left-hand corner, you see that blob. That's a subtour inequality in the inside form. The other one, like over on the right, that's a subtour inequality in outside form. Plus, they had all the no constraints. So that solved the problem. They knew that if they knew more about inequalities, they could solve bigger ones. But they didn't really press it in the 1950s because they were working by hand, and that's amazing that they did that computation by hand. They probably weren't going to solve any bigger problems by hand. But in the 1960s, it was popularized by Jack Edmonds, who was convinced that the only way to get a polynomial time algorithm for the TSP was to completely understand the inequalities, the tour inequalities. And Gomery thought that this is the way of practically solving the TSP. You don't need to know all the inequalities. You just have to get your hands on some of them. Get your hands on them, or Edmonds' theory to know the inequalities is you want to solve the separation problem. So you're given an LP solution X star. Does it satisfy all the TSP inequalities or not? All right, is it in a convex solid of points? So for the subtour inequalities, you could check by doing a min cut. I should point out that Folkestone, the Ford Folkestone paper came out in later in the year, 1954. The same Folkestone that worked on the TSP. He knew how to find cuts. The question is, can you find more complicated inequalities? All right, this was Strine's research, and this is what led us to and so we know how to do this quite well for problems around 50,000 points. So this led Keld and I to explore this 3D data set with some 2 million stars. Yeah, we can't solve it, but as I pointed in the abstract, we have a tour and a lower bound that come within a factor of 5 goose eggs and a 7. So very close to optimal. I should point out that those 5 zeros in the approximation, integer programming solvers by default, as soon as they hit a 4th zero, they stop. Say they're optimal. We're order of magnitude better than that. This is really precise precision. I mean, most things in the physical world you can't get. So the Olympic pool, I looked at it. What's the measurement for a 50-meter pool? It's less precise than this. Yeah, but it's not done. So we didn't. It's not practical anyway. So we're still using it to try to drive some further research. I should point out that this tour, in this case, it was found by Keld because we can't run branch or bound on this large of an instance. This is just a linear programming problem. So this article that appeared in the Sci-Fi Wire, the writer popularized a reward that we offered. So Keld and I had won 2 years ago $17,000 in the end of year Kaggle competition, and now 10,000 of that we're offering as a prize. So the tour is 28 million parsecs. If you prove by 1 parsec, we offer $50 up to a total of $10,000. You can't really. Our gap is actually 213. So I could have left that 10,000 out, but numerical errors. I don't want to risk my house on this. So far, of course, no one. I don't know why, of course, but so far no one has found it. But I actually would be delighted if someone found it, because I don't suspect that towards optimum. Keld thinks maybe it might be, but I'm not sure. But I would like to know, because that would influence how we work on the lower bound. All right. So what issues came up with such a large problem, a 2 million point problem? Well, yeah, I was just checking the clock. The first thing is it's big. right? And so it's kind of hard to run your normal algorithms on a 2 million point problem. Fortunately, in our Concord code with Applegate, Bixby, and Quatel, we had a procedure that scales up linearly. So we don't really know much about the TSP polytope. Even for 10 points, the whole convex hull is not known. But we do know how to solve small instances. We're good enough to solve instances, say, on 40 points. We solve very quickly. And there's a polynomial equivalence between the optimization problem, being able to solve something, and the separation problem, which is what we want to do. So we made use of that equivalence. Not using the ellipsoid method would mean we implement it with the simplex algorithm and column generation, but it's motivated by the equivalence of separation and optimization. So we take our LP solution, and we're going to map it down into a much smaller space and apply separation is equal to optimization. So what we do is we first do some pre-processing, shrinking certain sets that we know don't keep us in the convex combinations if they're present. And then we pick a point and do a breadth first search in the LP solution, find a local neighborhood of around 40 to 50 points. And then we shrink the rest of the world down to a single point. So shrinking the rest of the world means that in the map space, we don't quite get a TSP. We have a multiple TSP where that one node can visit more than once, but we can solve those. And that produces inequalities for us. So as I said, we always did like 40 to 50 points over the years. This was in the about 10 years ago, we had this. Over the years, I've tweaked the code, not major changes, small tweaks that allow us to go up to sets of size 100. We're doing optimization, separation on subregions of size 100. And that scales up, great. All right, but then comes the next thing. So the workhorse of the TSP and indeed operations research is the simplex algorithm. Now we're running into difficulty though at this scale. So the simplex algorithm for this particular 2 million point problem, I took a sample from our log file from earlier this week. The simplex solver is taking over 99.99% of the time. All right, and so all right, you have to solve one LP. What's the problem? It's taking less than a day. The trouble is the cutting plane method is sequential. You find a solution, cut it off. Find a solution, cut it off. For that Netherlands problem, the 57,000 points, we did about 57,000 LPs. We tend to do about N LPs for those hard problems. So in this case, you're doing 2 million, and we're taking a couple of algorithms that, well, as I say, you can do the math. So we have two problems: the sequential nature of the simplex algorithm. There's no effective way known to parallelize it, and the sequential nature of the cutting plane method. So the simplex method said, well, why don't we replace it by the barrier algorithm? They parallelize, which is true. But we want to solve a sequence of LPs, and barrier methods aren't really great at that. Simplex method is. All right, so we just say, all right, well, we can't do the problem. Yeah, but yeah, that was the point. I didn't want to be able to do the problem. I wanted to be able to discover things. All right, so we didn't know how to do it, and so we just came up with a silly method. Now, if you have a silly method, one thing I learned from the machine learning community, if you have a silly method, at least describe it with a pretty picture. So yesterday I made this colorful picture to describe the silly method. So we don't know how to solve these LPs. Simplex method takes a long time. So I just do randomization. I just run 32 with changing some random seeds, so they'd run slightly different. The cutting plane method, the simplex solves will go in a slightly different path. Then at each night, I burn down 28 of them, right, and restart them with the best. I keep the best 4, and I restart the other 28 with the best one. But I don't throw away the information. Those LPs all contain carefully selected inequalities in their final LP. I gather them all together to a pool and feed those to all the new ones. All right, so there's no theory, nothing behind this, but we didn't have anything that we weren't making any progress, and this allows us to make progress. Okay, that's the sequential nature of the simplex method. We try to get around it with a silly method. Getting around the sequential nature of the cutting plane method, that's simple, but I don't think it's silly. You have this geometric problem. So what we do is we first partition the space we partition the space, then we look at overlapping regions, and finally we look at random regions. You pick a point and take the random, say, 50,000 neighbors at that point, and completely run the cutting plane method in those till it stops, until you're not making any more progress. So what's the point is that we take the final inequalities from those random regions. So we run 320 processors. all running on these random regions, take all the final inequalities, and that's done the selection for us. That's gone through this long process, sequential process, but on small examples. And we feed that in, and that sort of burns away the sequential process of the main cutting plane algorithm. So that's what gave us the bound. Okay, but there was one big weakness, and that is there's a certain class of inequalities that, together with local cuts, is what drives the solution of those map problems, those 50,000 point map problems that we can't apply. And so I want to describe that. So the subtler inequalities, they're quite simple, and they're the building blocks for another class of inequality called Coleman inequalities. So Coleman inequality, rather than taking the cut set from a single set, you take this Venn diagram like I've drawn. The set H is called a handle. The three rectangular sets are called teeth. You add up their cuts. That should be at least 8 because they're subtler inequalities. But in fact, it's at least 10. That's called Coleman inequalities. They were first developed by Quatel in 73 and then generalized by Grocho and Padberg in 79. I should say that Quatel did his work at Waterloo. He was a postdoc, greatly influenced by Edmonds. I looked at his paper this morning. He actually thanks Nash Williams, Crispin Nash Williams, for directing him to apply LP methods to the Hamilton cycle. So we have Nash Williams to thank for Coleman inequalities, which lead to Concord. Okay, so early on in our TSP work, so when we first started working with Boschek and David Applegate, we focused on combs. Now combs had those sets called teeth, and they have part of the regions in the handle and part that's not. So that naturally forms what we call a domino. You take two sets, A and B, that are unions on the whole set of points, and they're disjoint, called a domino. These all have 2's. Forget about those 2's. You can see me pointing at the screen. I saw this earlier this afternoon. I forgot to take them out. They're supposed to be subtler elimination constraints that I'm adding up. I shouldn't have those 2's there. I first had them greater than or equal to, then I switched them to less than or equal to, and I forgot to delete the 2's. All right, so they're supposed to be subtler elimination constraints. So that should be the point inside of A union B is at most A union B minus 1. You add those together, you get what's the domino inequality, which is correct. You get some inequality that's satisfied by all tours satisfy that domino inequality because it's just a sum of 3 subtours. All right, from that, you can build a system. You put all the domino inequalities together with equations and together with variables that have to be greater than or equal to 0 that we write as minus x is less than or equal to 0. And from that, if you take any non-negative combination of those inequalities, you get another inequality satisfied by all tours. So let's take a 0, 1. We'll just add together some subset of those inequalities. Well, that gives you inequality valid by all tours, but it's of no use, right? You might as well just take the original inequality. But if your right-hand side, so these A's in your inequality, the left-hand side are even, and the right-hand side is odd, well, then you can improve that inequality. You can decrease it by 1, the left-hand side, right? Because you have something that's even, you're less than or equal to odd, so it's less than or equal to odd minus 1. That then gives you an engine for producing TSP inequalities. Just do these solves over GF2. You literally do Gaussian elimination, produces you inequalities. All right, and this is what we strove to take advantage of early in our TSP work. All right, so it's useful to examine what that parity condition means, right? Most of the stuff in the system is even. Look at the right-hand sides. They're even numbers except for the domino inequalities are odd. So if you're going to get a GF2 inequality, you need an odd number of dominoes. You're taking an odd number of dominoes. All right, and the dominoes have, most of them is even, except for the semi-cut, the part that goes from A to B, that only has value 1. All right, so if we let D be the set of dominoes, and we let H be the set of vertices that have value 1. So we're adding up the degree constraint. That gives a set H. Well, what do we have? We have to, at any point in any edge inside of H, is being hit twice at the value of 2. It's even. But the edges in the cut have one end in H, one end not in H, so a cut defined by H, delta of H, that's odd. So if you're going to get everything to be even parity, what you have to do is this set of edges that you use from the x less than or equal to 0, so the set F, and the set of semi-cuts, the edges that appear an odd number of times in those sets has to be exactly delta of h. Or so then you don't need that parity constraint. You just need to say that you have a set of odd number of dominoes, and you have a set of edges f, such that the odd ones, the edges that appear odd number of times in those sets, gives you a cut. All right, that we knew. And so we look back at the Coleman inequality. You put exactly in that format, right? The Coleman inequality have disjoint dominoes. The set f is exactly the edges that are in delta of h, but not in one of the semicuts. So you put that together, you get inequality less than or equal to form. Using the three equations, you can change that to greater than or equal to form. That's where you get this, well, for 3 teeth, it's greater than or equal to 10. For k teeth, greater than or equal to 3k plus 1. All right, we knew that. And this is I quoted from our paper because it's a big mistake. I mean, it's okay, it's a while ago, but we were fixated on combs. We wanted combs. And you look at our thing, we had this notion of a cutter. We say you're finding an odd number of dominoes such that they get an edge set, except for we wanted the dominoes to be disjoint, right? Because that gave us cuts. And that in retrospect is a mistake. And we were only saved by the brilliance of Adam Ledford and the tenacity of and brilliance of team led by Sylvia Boyd. So Ledford looked at this and said, that's crazy. I mean, they're just thinking, well, it's a cool Venn diagram. They want combs. Algebraically, it's much nicer to just look at all the inequalities you get. They call them domino parity inequalities. Had this nice compact form. And I knew about that, but when the paper came out, I thought, well, we don't want those. We want combs. So even he gave a polynomial time algorithm to find those in the class when the your LP solution supports a planar graph. Now, they don't quite support planar graphs in general, but for geometric problems, but they come close. It's a very, very good case. Still, we didn't do anything with it. Sylvia Boyd led a team in Ottawa, though, and they did do something with it. They, on medium-sized instances, so about 500 points, they sort of did a woman-machine type of method where they did the transform to a planar graph they did by hand. Then they had a computer code to do the rest. And they showed that they were effective on these instances. Based on their work, that's finally when we jumped in together with Marcos and Danielle. Marcos and Danielle spent a lot of time during our years at Georgia Tech trying to prove this, and we still do that. The only reason we can solve those 3 large instances is because we got even further improvements to our algorithm. Let me try to describe just in a few minutes this polynomial, this planar algorithm, if I can. How best to do this. So click to share. Well, first switch the video to the blackboard, which Henry likes the best. Then stop the share. There you go. All right, I pre-drew a couple of graphs on the blackboard. The one on the screen's left is where we get the domino. So the dominoes have 2 sets of nodes. There'll be the red ones and the blue ones. So I'll put one red node. By the way, this is this really expensive chalk from Korea, but you guys are worth it. And we have blue nodes. All right, so that represents a domino, A and B. All right, so we have certain types of edges then. The most important edges are the semicut. So I'll draw those in these squiggly. That's yellow, though it doesn't come out. I know it doesn't come out so well, camera, but I make them squiggly. That's the semicut. Then we have the edges that cross the red region. So they have one node's red and one node that's not red. All right, and then we have the edges that cross the blue region. So it has one end blue and the other end not blue. All right, so they're the important edges in the cut. Now, what's great about planarity, of course, what you have to take advantage of is that planar graphs has duals. This one, you have a vertex for every region. So here you have the outer face, but then you have 8 faces on the inside, which are the important ones. So let me jot those down. So the dual graph, planar dual graph, has the graph has 8 faces. This has 8 vertices. So then it has the edges. So there are those yellow edges. They go between the middle vertices. So they look like this. the red edges go from, like this red edge is crossing the two outer from the middle row with the top rows. So they look like this. And then between the two top faces, looks like that. Then the blue, there's 4 blue edges. They go from the ends on the bottom, and then between the bottom rows, they look like this. All right, then there's some other edges that aren't in the cuts. So like that edge appears there. Then we have the outside face, which goes to those nodes and those nodes at the bottom. All right, so that draws the domino in the graph. And what's important is that you see that the semi-cut is a path in the planar dual, and so are the other dominoes. Right, and this just follows from the looking at that you're getting cuts. So that allows you to find dominoes in a planar graph by looking at min-cost flow between S and T. Do 3 successive shortest paths. That's great. Dominoes you could find actually in polynomial time, but a high order polynomial. This allows you to quickly find them. Wow. It's so expensive, but it allows you to find them. But the bigger point is that you can piece those dominoes together to an inequality. So what do you want? You want those cut sets, those semi-cuts, to form this cut set. So what you want then in the dual is to form, you want the semi-cut, which is those paths, you want it to form together with some edges an Eulerian subgraph, right? Because cuts go to Eulerian subgraphs. So this path you get from S to T, you don't care about the middle points because they're even already, just care about the ends. So you could represent the semi-cut just by drawing an odd edge in a dual. So something like this, you add to your graph, to your dual graph. This is an example of a dual graph. You just draw some odd edges. Now to find a domino parity inequality, you want to find Eulerian subgraph. So you just solve the minimum weight odd cycle problem, right? You might find something like this. And then the odd edges, the yellow ones, those give you your dominoes, and the normal edges give you your set F. All right, so they give a polynomial time algorithm, actually fairly simple. I mean, once you work that out, but it's like a candy shop where people are working algorithms, right? To try to make this work on 100,000 points, right? You have these min-cost flows that you have to do all over the place. And the most important thing is the planarity. The graphs aren't quite planar, and you have to somehow transform them being planar while keeping the inequalities. So let me go back to the unreal world of the, oh, there I am. All right, let me try to reset things again. So the first thing would be to turn the virtual camera back on. Next thing would be to share the screen. Share with Keynote, if I can find it. Keynote. Okay, but for these 3-dimensional graphs, they're not planar, right? And so it'd be great if somebody could work out how to do this domino parity in general polynomial time algorithm, or on some graphs that go beyond planar graphs. Even slightly higher genus surfaces could be quite useful. All right, but so what we did then end up doing over the past couple months is to go back to our original plan of looking at GF2 systems, right? And this time not worrying about combs, just going for domino parity. All right, so what is useful is that if you look at the form of the domino parity constraint, that implies that the dominoes have to be nearly tight, meaning the cut sets, the 3 cut sets, A, B, and A union B, have to be within a factor of 2 of a minimum cut. So cuts have value at least 2 because they satisfy the subtor constraints. And you can enumerate all of those. All right, so that means that we have a technique for producing the inequalities. And now how to find a violated inequality? Well, we wanted, the inequalities can be violated most by 1. If you're only looking for ones violated by 1, then you can literally do Gaussian elimination, right? You just only put in the tight ones. So anyone you get is going to be violated by one. And so that we do, and we generate those cuts by a combination of heuristics, the randomization algorithm of Kargar, and most importantly, an exact algorithm by Nakamuchi et al. For generating all subsort cuts. All right, now that's for generating maximally violated one-to-ones. To generate maximally violated ones, so ones that might be violated less than one, we use integer programming. All right, so you replace the parity conditions by modeling out with integer variables. All right, so there's two ways of doing that. You can do it the straightforward way of having variables select H, variables to select the dominoes, and then parity conditions on the edges. Or you can do the cut formulation where you get a spanning tree and look at the fundamental cycles and get the get the characterization of cuts and implement that in integer programming. Actually, the way we do it so far, it's been a simpler method, seems to work faster. So these LPDOs are hard to solve. So what we do is we use the machinery of what I coded in the past few weeks. So I used the machinery of local cuts, get local cuts with regions of thousands. So I take the best LP, this one that gave us bound with the 5 goose eggs, take that best LP, look at regions of 1,000 points. Over the past 2 weeks, I had 320 processors, all trying to find cutting planes using mixed integer programming, and it's found 615,000 of them. Most of them are not combs, most of them are general, and with a lot of violations. Some 13,000 of them are maximally violated. What to do with that big treasure trove of inequality is not clear, but the main point is that they exist. And so now we'll be aiming to find heuristic algorithms to actually produce them, or exact algorithms would even be better to produce them. Okay, so a lot of this was all geared around how to do the simplex method. If we go up even higher, the simplex method has no chance, right? The simplex method is at its limits. So those points there's 2 million points for Gaia data release 1. Gaia data release 2 has 1.3 billion points. So another factor of 1,000 larger. So looking at the 10,000 of those, what we did, we aimed to solve 1 LP. Actually, for 10,000, it did 8 LPs, because, well, why not? Because we could do them. We gather as many cutting planes and also as many variables that we find are important. Remember, there's n-squared variables. You also can't list all of those. And for 10 million, we're able to exactly solve those LPs, or close to exactly solve those LPs with the commercial barrier codes, interior point methods. They run on 32 cores. Each took like 3 days, maybe to 3 or 4 days to solve, which is acceptable. What's problematic is that they took 700 gigabytes of memory. So once we go up to 100 million, we couldn't use that. But for that case, for 10 million, we still got the 4 goose eggs, and I think we can do better as I learn more about what cuts are important. For 100 million, we can't do the barrier method. That's where Google and Dave's team at Google comes in. They have developed a first order method to give a very good approximate solutions. For us, that's good enough. I can take approximate solution, I make it into a feasible solution, and I get my bound. For 100 million, we're able to get 0.007, and I think we do much better than that. That they're still stepping up their algorithm, and I'm finding better. I supplied them with better cutting points. For 1.3 billion, we're not able yet to solve due to first order method, but that's the goal. I actually don't know what application Google has in mind for this such a big problem, but they're using this as a TSP as a sample problem to do this. Right now we have approximately just 2 goose eggs, but this is not solving any LP completely. This is just piecing together geometric subproblems. But that's the goal, to see whether LP method can scale to 1.3 billion. Okay, let me, good, I stopped the time because I wanted to do one last thing, is to share a different screen. Let me see, new share. This one. All right, this is all right, there it finally appears. So this is a web page. So it's available from my homepage. And again, it goes back to this notion that only the simplest example could solve. So this is 50 random points. And completely in the browser, so it's running on JavaScript. It's not running on some server, it's running on your machine. You can go ahead and solve the LP, like the full subtor LP. So it's completely done with JavaScript. Well, the LP solvers are C code that I made an interface to Java can call it, but it's running completely on your browser. You can even get the dual solution somewhat similar to the Danzig et al., but using the Pouilly-Blanc and Younger geometric zones and modes. You can draw that. It was just a lag on Zoom. It comes up immediately. So you get the dual solution. If I get the LP solution, well, you can also add cutting planes by hand. So this comb, if you want to build a comb, the simplest cone should have a handle and 3 teeth. So a handle, the natural thing is these fractional edges, that value half. I'll put all those in a handle, and now I have to get 3 teeth. The first one will be these bright blue ones. T2 will be, so these will just be edges, so sets of size 2. These are the dominoes. Now that's a comb, I can add it. It was violated by 1 and improves the LP bound. All right, so I mean, it's more fun than Tetris. So if you're looking to kill time, or you're looking to teach somebody, even really young person, how to do solve the TSP, this is something you could use. So if I do the subtotal LP, you can also do branch and bound. That in branch and bound, rather than any cutting planes, you take a fractional edge. So these ones are value, black ones are value 1, the red ones are value half. I click on that. It'll split that into 2. So it'll force the variable to 0, and then force that variable equal to 1. Now the LP solutions might not be connected. You can add cuts, subtotal inequalities, make them connected. So I split that parent problem into 2 problems, and you see the bound went up. So I'm going to branch on that. And that way I can build a search tree. So you then pick by hand, you pick the next problem, branch on that, figure out some red edge to branch on. You create the child subproblems, add the cuts if any, and then branch. So if I go back to the full LP, you can also just see how it runs. If I just let the computer do the branch and bound for you. So it just repeatedly splits the problem into 2. And of course, that's going to be finite because it keeps setting things to 0s and 1s. But why it's way better than finite is that once you have a linear programming bound that's bigger than your Tor, well, there's no point searching anymore in that tree. So this is the optimal solution. This blue node down here, this gives you optimal Tor. If I pick one of the interior point nodes like this one, that LP solution was branched. So I split that one into 2. If I pick a leaf node that was not a Tor, it was pruned. The reason it was a prune because its bound is bigger than the Tor. That gives you a way of solving the LP. Okay, so if you're interested in teaching branch and bound and you'd like to use this, I'm welcome to, I'm quite happy to give you more advice on it. Anyway, it's just a summary. If you want to see pretty pictures, by the way, I spent a long time making this, by the way, this app took quite a few hours and quite a few days in the fall. In the spring, I spent quite a bit of time drawing these 3D pictures, which if you go to the website that appeared on the screen, if I go back to the old share, Keynote. If you look at my homepage, or you go to that link there, you'll see there's 3D drawings where they spin around, and I should have been proving lemmas, like I'm sure everyone in the department was doing during the beginning of COVID. I was figuring out how to push through 1.3 billion points. That's a lot of data, pushing it through a GPU in order to spin around the Tor. And so you can say, I think the pictures are pretty. I tried to show them on Zoom, but the lag didn't allow me to do that. Okay, that's all. Thanks, everybody.
Thanks, Bill. So any questions? Please unmute yourself and feel free to ask any questions.
Somebody's saying something. I can hear it.
Bill, did I understand you correctly when you said that you weren't sure what the application for Google was? Are they?
I don't know why they're calling the 1. I don't know why they want to solve a 1.3 billion variable problem. You know, the employees aren't able to say that, but I mean, they certainly have data sets that big. What they actually want to do, I don't know.
But there are big problems like that in finance. People are solving large problems like that because there's so many
They're
scenarios.
solving linear programming problems with 1.3 billion variables.
With billions of variables and millions of constraints. Yeah.
Yeah, then it must be pretty special because there's no way that they have a general LP solver that can handle 1.3 billion variables.
So there's a question from Joseph Cherian. What is the smallest known family of natural examples not solvable by software?
Yeah, that's kind of a hard question because once you post a code like Concord, we do a lot of settings that we are made so that a typical example solves well. And so what people have done is taken the Concord code, the main people have done this, the most successful people doing that were in Bonn by Stefan Hogarty and the student. They have some examples that are bad for the 4/3 conjecture. So they meet the 4/3 bound. So they're just some easy geometric patterns to them, but Concord's cutting plates just aren't effective on those. It doesn't mean that with some small changes to the code that they could be solved. They're definitely not hard examples. What they are is for that specific computer code, they're hard for that. So I think they have points even, they can create an example on like 250 points that they let the default Concord run for like a week and did it solve. So in our, so that was artificially created. When we do this local cut procedure, we're doing separation optimization, we're solving lots and lots of small problems. Every now and again, we find some small one. It's not geometric, it's just a matrix of data. But we find small examples that the Concord has very difficult. So even on 50 points, that Concord is very difficult to solve. So I have to go in and look to what I need to change to solve those. So Concord doesn't show that P is equal to NP. What it shows only is that you have to look hard to try to find examples where it doesn't do well. But it's certainly not doing everything.
Okay, other questions? All right, so maybe we can have more discussions after the seminar in the social chat. So let's unmute ourselves and thank Bill for the talk.
Thanks, everybody.